Hey guys, welcome to Nth. It's not that hard. Today we're just gonna do U-Sub. It's kind of a basic review, but this is a concept you should know like the back of your hand for calculus AB and BC. It's critical to understanding how to do integration, and probably your first instinct, or it should be your first instinct whenever given an integration problem. So here we go. This is a very typical example of something you're gonna get. So integral of 3x plus 9 cubed dx. We're going to use U-Sub to integrate this because how else would you do it initially just looking at it? Because if you just take the antiderivative of this, you'll find that it won't work because this inside isn't just like x. So if it was something like, I don't know, like 9x squared, that you could just do very simply, just, take out the 9x squared, my bad, x squared, there's a dx here, dx, and you just antiderivative, it'll be 9 times x to the third over 3. That's simple enough, but you can't do that when there's something on the inside. So what we have to do is this topic called U-Sub. I'm not going to go through the proof or anything in this video. I'm just going to give you a straightforward quick review on it. So whenever we're deciding what U is, this works for U-Sub and integration by parts. We have this acronym called LIATE, and it goes logs, inverse, trig, algebra, trig, and exponentials. And then this is the order in which you should decide what your U is usually, or in integration by parts, U and dv. It doesn't matter too much here. For me, what I would just do is just look what's the most obvious big part that we just want to get rid of. So if we look at this, the most obvious big part that we want to get rid of is this, 3x plus 9. Because that's what's giving us trouble. Because if this was just x, it would be easier. Or in our case, if it was just u, it would be easier. Because then we could just use standard anti-differentiation. So what we're going to do is we're going to take this and we're just going to reassign u as 3x plus 9. Simple enough. And then now what we're going to do, we're going to take the derivative of u, in other words, du. And then if we take the derivative of this, we're going to have to take the derivative of this as well. Derivative of 3x is just 3. Derivative of 9 is 0 since it's a constant. And it's not just 3. Be careful, it's 3 dx. This will become important later. And then we are going to plug these into our integral. So in other words, we're going to say this integral is equal to, we said 3x plus 9 is equal to u to the third. Oh, but the problem here is we don't have, anything to plug in for our dx. What we do over here, what you gotta do is divide both sides by 3. So we can do that. Basic algebra. And we have dx is equal to du over 3. Simple. So plug this in, plug and chug, du over 3. And from there, it's just classic anti-differentiation. So you treat this almost just like a regular variable, and then we'll deal with this at the end. So I like to pull out this 1/3 over here and put it over here. So this is another way of writing it. Normal anti-differentiation is going to be equal to 1/3 u to the fourth. We add 1, we add 1 to the denominator. So u to the fourth over 4. And then we don't have any bounds, so we're just going to say plus c. And then, on the AP, this is an acceptable answer. Don't simplify when you don't have to. And in other words, this is just u to the fourth over 12 plus c. This is what we're going to get at the end. But wait, we need it in x, not u, in terms of x and not u. So what do? Simple. We just plug this back into here. So the integral, because this isn't going to be the integral of this. Because whenever you take an integral of something, it needs to be in the terms, or with respect to x, or with respect to whatever is here. So if this said db, we're going to do respect to b. dy with respect to y. It's dx, not du. So we're going to plug in our u back, and then we're going to get as our final answer 1/3 times 3x plus 9 to the fourth over 4. This is a really sloppy 9. And then never forget your plus c with indefinite intervals. So this is our integral. Simple enough, nothing too complicated. Let's move on to the next example. Okay, we're gonna have another example here. This one looks a little bit more complicated, but we just do our steps and it's gonna be easier. So again, we could follow Liate. What do we have here? We got an exponential with this e, we got an algebraic, and that's about it. Algebraic, a is higher than e, so that means that's going to be our u value. So u is going to be an algebraic. We could choose x squared or x. Remember, always go with whatever is bigger and more annoying, so this x squared here. So we're going to call u as x squared. And I'm just going to get rid of this. And same steps. What do we do now? Take the derivative of u, du. Take derivative of this side, 2x dx. And now, last step, rearrange for dx. So dx is going to be equal to du over 2x. And you might initially think, wait a minute, we have an x in here. That's going to get funky later. Actually, it'll help us actually to make this x here go away since we don't have anything to replace it with. Because it would be more annoying to reassign this as like u or root u is equal to x, because then you kind of just get what you started with, but more annoying. So let's rearrange. Let's plug in. I'm going to take this 5 and put it on the outside. Kind of wrote that a bit big. Okay. Take this 5. And I just accidentally erased this. There we go. My bad. And at 5, we're going to keep the x there because we have nothing that's equal to it. Times e to the x squared we said is u. And dx we said is du over 2x. Now this is where this x becomes useful. X, guess what? They cancel. Get rid of those x's. They're useless now. And we just have a 2, so we're gonna, rearrange e to the u and du. And then now you get classic example of your best friends on the AP, which is e to the something. Because derivative of e to the x is just e to the x. Derivative of e to the u is just e to the u. So, this is 5 over 2. E to the u. Plus c. And that's our answer, right? Nah. Correct. It is not our final answer. We just got to plug in this u back and then we're done. So our actual final answer for what our derivative is the same thing. So 5 over 2 e to the x squared, because we plug in that x squared, plus c. Wow, looks so much nicer than this, right? Doesn't matter. This is our answer. It's the AP. Don't simplify anymore. I don't know how you would, but you can keep everything in the parentheses. Cool. So that was 2 examples with indefinite integrals, meaning no bounds. Let's do an example with definite integrals, and I'm going to show you 2 ways to solve it. And I'll show you my preference to which one. I'm just going to write the problem now. Okay. Now we're going to do this example. So only difference between this example and every other example is that now we have bounds. So this is a definite integral. So there are 2 ways to solve this relative to the bounds. I'm going to show you the, I guess, more annoying way first. And then I'm going to show you what I would prefer to do. So same thing as before. Liate, there's just algebraic here, so there's nothing to think about. So we just have to pick the most big, funky, annoying one, which in my opinion is x third minus 9. So u is equal to x to the third minus 9. Take the derivative of du, of u, so we get du, so 3x squared. Derivative of 9 is a constant, so it's gone. And then don't forget your dx, very important. Next thing is writing and rearranging so that dx is on its own side. So dx is just equal to du over 3x squared. And we saw in the previous problem that having an x in here is perfectly fine. So let's plug in and replace with our new reassigned variables. But I'm going to hold off on these the balance for a second. And we're not going to set it equal to, because these are technically not equal to each other, since we're not going to have bounds. So 6 stays the same. We're just going to put that on the outside for ease. You can always do that. It's just multiplication. And x squared, keeping it, because we have nothing in here that can replace to go to x squared. And then times x to the third. Oh, minus 9, that's u. U to the fourth. And then dx, what did we say dx is? It's du over 3x squared. And same thing as before, thanks to this dx value, we can get rid of this x squared. They cancel out. 3 over here, this also cancels out, 2. So we can rearrange this and just call it 2 integral u to the 4th du. Nice and simple, easy looking. And then, same before, find antiderivative. That's just, or it's going to be equal to 2 times antiderivative of u to the 4th is just u to the 5th over 5. And plus c. Or you could probably save the plus c to the end, but it doesn't really matter. They're not going to mark you off for that. So we're done, right? Nope. 2 steps we're missing. We're forgetting our bounds, so we actually evaluate, and we didn't plug in x squared. So this is where this branches off into 2 separate ways of solving. So let's just do the conventional way, which is just immediately plugging this back in and then using the bounds they give you. So I'm just going to write over here, now equal to, since we're using the same bounds, since we're going to plug back in x, it's going to be 2 u to the, or not u, my bad. It's going to be 2 x to the 3rd minus 9 to the 5th over 5. And then your bounds are going to be 1 to 3. So this is the AP. We don't have to simplify, thank God. So all we got to do is just plug in your bounds and then take the difference of the next 2 parts. So 2 times top first you plug in. So 3 to the 3rd minus 9, and that's to the 5th, over 5, minus plugging your bottom bound, 1 to the 3rd minus 9 to the 5th over 5. And you're done. That's your answer. But honestly, in my opinion, this is kind of clunky and annoying, and it's really ugly, but perfectly acceptable AP answer. You shouldn't simplify past this because you're only going to hurt yourself. Now I'm going to show you the alternative way, which is going to involve taking from this step here and changing it. So we're going to have our integral again, which was 2 u to the 4th du. And I'm just going to remind ourselves what our u values were. So our u was x to the 3rd minus 9. Du was 3x squared dx. And dx was just du over 3x squared. So what we, and in our original bounds were 3 to 1, or 1 to 3, my bad. So in here what we did was that we plugged back in our u and then we dealt with our bounds. There's actually, in my opinion, an easier way where we just deal with our bounds from the start. And the way to reassign our new bounds so that we can actually just integrate with respect to u instead of x is to take these bounds and then plug them into our original u function here. Reason being, these values, these bounds are in the with respect to x. If we have u is reassigning what our variable is and what we're taking the integral with respect to. So now if we're taking it with respect to u, we want what our initially x values were in terms of u, which is what this does, completely converts it. So plug this into here, plug that into here. I'm gonna pick a different color just to show you there's a different way of solving it. So our initial value is 3 to 1. We plug it into u. So we'll just get rid of this for now. Plug it to u. Oh, I completely just erased this, didn't I? 6. There we go. It was 1 to 3. And what we're going to do now, we're just going to take these bounds, plug them into here. So u is equal to 3 to the 3rd, or let's call u2 as our second bound. 3 to the 3rd minus 9. You don't have to simplify, but you can if you want to. So that's 27, that's 18. And then u1, let's plug in this 1 to the 3rd minus 9, that is negative 8. So these can be used as our new bounds, and we could take these new bounds and then plug them into here. And then what we get, we remind ourselves, this as well. Can take these new bounds and put them here. So now we get 18, and then we get -8 du. And what we could do now, easy enough, is take the integral with respect and the antiderivative with respect to u. Since we have bounds, it's a definite integral. And these is equal to this. And you're going to see that in our final answer. So we'll just write it down. So 2 times antiderivative of u to the 4th is just u to the 5th over 5. -8 to 18 is our bounds. And this is just equal to 2 times 18. Oh, let me just view. My bad. 18 to the 5th over 5 minus -8 to the 5th over 5. And if you're going to plug into your calculators, you're going to find these two are the exact same thing. They're equal to each other. Personally, I prefer this way with reassigning our bounds, just because, you know, there's less room for like stupid like mistakes like miswriting or forgetting a negative sign. Either or works, they're perfectly fine. They're acceptable both on the AP. I recommend the second way, but that's purely up to you. And that took a little bit longer than I thought. Sorry for the little mistakes here and there. Overall, that's just U-Sub. I hope you understood. Leave any feedback in the comments, and yeah, bye. Good luck.